Hi there, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. Today, we're going to go over our third question from Circular Motion. This will be the last question we do on Circular Motion, so hopefully out of these three problems, you got a pretty good review. If not, go watch a flipping physics video or go over, redo some of these problems, see if you can do them again. But we got to keep on chugging along with the rest of our units, okay? So let's take a look at this problem. A coin C of mass 0.005 kilograms placed on a horizontal disc, and the distance from the center of the disc to the coin is 0.14 meters. The disc rotates at a constant rate, counterclockwise as seen above. The coin does not slip, and the time it takes for a coin to make a complete revolution is 1.5 seconds. Okay. So they want us to, the figures on the next page, but they want us to draw and label vectors showing acceleration and velocity for the coin when it is at the position shown. So this coin is undergoing circular motion, and we know that in circular motion we have a centripetal force that causes centripetal acceleration. Now remember, centripetal means pointing towards the center. So they didn't ask for the force, but if they were to ask for the centripetal force, it would be like this, but this is the centripetal acceleration also pointing towards the center. Okay? Now what about the linear velocity? Meaning, if this were to stop rotating, which direction would the coin go? And remember, for circular motion, the linear velocity is tangent to the circular motion. Okay, so if here's the circle it's going to move around, it's going to go tangent to the circle. So this is the linear velocity of the coin. Perfect. Determine the linear speed of the coin. Okay, so we need to determine the linear speed of the coin. Well, we're trying to find v. Okay. Now, what they gave us was, they didn't give us the linear speed. They gave us the time it takes for the coin to complete a revolution in 1.5 seconds. Okay? That's the period t. Okay? And we know that the angular velocity is equal to 2 pi over t. Okay? You can find this on your equation sheet, right? The angular velocity, omega, is equal to 2 pi over t. Okay? And we said 2 pi, and this is 1.5. Okay, actually, I don't want to solve for that yet. Hold on. Let me erase this. Okay. Now, we also know, something that I also know, is that the linear velocity, right, is equal to the angular velocity times the radius. Okay. This is not on the equation sheet. This is something that you have to know, but since the test this year is open note, I would add this on your equation sheet. Okay? All the linear quantities are equal to the angular quantities, just times the radius. Right? So velocity equals, linear velocity equals the angular velocity times the radius. Okay? And since we know that the angular velocity equals this, I can just take this and plug it into there and write a new expression, which is the linear velocity is 2 pi r divided by the period. Now let's plug in numbers and let's solve. This is 2 times pi times the radius was 0.14, all divided by the period, which was 1.5. And when we do this, I get about 0.59 meters per second. The rate of the rotation of the disk is gradually increased. The coefficient of static friction between the coin and the disk is 0.5, determine the speed of the coin when it just begins to slip. So earlier it says it was spinning at a constant speed, but then now we're saying, okay, let's spin it faster and faster and faster. Okay, if we're looking at this kind of disc here, here is the coin. Okay, it is friction that is causing the centripetal force, right? Or the force that causes this to go in a circle is the frictional force. If there were no friction, this coin would just slide off. It would not. It would slide off in this velocity direction. Okay, but because there's friction, it allows it to go in a circle because it's a center pointing force, the centripetal force. Okay, so let's figure out. Slipping happens, just begins to slip. That happens when we reach maximum. We have reached the point of maximum static friction. Maximum static friction. Okay, we've reached the maximum amount of friction that we can get, and so we have overcome that, and that's when we begin to slip. It's maximum static friction. Okay, so for this, we will need Newton's second law for centripetal motion, or circular motion, which is centripetal force equals mass times centripetal acceleration. What did we say the centripetal force was? It's the force of friction, and since it points towards the center of the circle, it's positive. And we're going to do mass, and if you remember, centripetal acceleration, you can find this on the equation sheet, is equal to v squared divided by the radius. Okay. Now how do we break down force of friction? On a flat surface like this, force of friction you can break down to mu times force normal. This is mv squared over r. And force normal, we can break that down, since it's on a flat surface, to mg. If it were on an angle, we would have to make it mg cosine theta. Okay, and this is equal to mv squared over r. You'll notice that there's mass on this side, mass on this side. We are trying to find the linear speed or the linear velocity, so let's rearrange this for velocity. To do that, we would get mu times g times r square rooted equals the linear velocity. So what is that? Mu was 0.5. Gravity is 10 or 9.8. You can use the other one. And the radius was 0.14. That should... Oh, let's not do 2 equals 17. So velocity equals this, and this equals 0.84. So that is, if we go faster, any faster than this, the coin will start to slip off. Because at that point we have overcome the maximum static friction. Okay. In the experiment, were repeated with a second identical coin glued to the top of the first coin. How would this affect the answer to part C? Explain your reasoning. Guys, we already did the hard work for this. We already found the equation. We can see that the velocity at which it slips depends on these three things. Depends on gravity, depends on the mu, the coefficient of static friction, and depends on the radius. It does not depend on the mass. And so if we double the mass, it should have no effect on the velocity when the coin begins to slip. And that is proved by our equation right here that we found earlier. Since mass canceled out, mass has no effect on the velocity at which the coin begins to slip. Okay? So it would be the same, but the reasoning is because, according to our equation, the only things that The velocity at which it slips is coefficient of static friction, use of S, the acceleration due to gravity, and the radius. Okay. Cool. Hopefully you guys did well on that. Your couple things are due this week. You'll have another pre-response question due this week on Friday. Also due Friday is a picture on Flipgrid. You can find the link to that on Google Classroom. All right.